Edexcel Core Pure, Hyperbolic Functions 1, an Introduction, differentiating and integrating hyperbolic functions. So we've done some work with these hyperbolic functions, but what we need to think about now is how might we differentiate and therefore move on to integrating hyperbolic functions. So if I wanted to differentiate cosh x, for example, I could think of this as the derivative of, and go from cosh x to its definition, which is e to the x plus e to the minus x over 2. So differentiate e to the x is e to the x, differentiate e to the minus x is minus e to the minus x, a little chain rule there, and then we end up with the standard definition of sine of x. So the derivative of cosh x is sine x, which, notice, isn't behaving quite the same as trigonometric differentiation. So using that definition of cosh has allowed us to differentiate cosh to get to sine x. And it would seem a logical step now to ask ourselves, what do we get if we integrate sine x with respect to x? So if the derivative of cosh x is sine x, the integral of sine x is cosh x. Similarly, if we wanted to differentiate sine x, we can use the definition of sine, and when we come to differentiate this e to the minus x term, it will, because of the chain rule, produce another negative sign. So it's half e to the x plus e to the minus x. So the derivative of sine x is cosh x, and again it would make sense to think about integrating cosh x at this stage. And if you integrate cosh x with respect to x, you will indeed get sine x. So we now have a way of differentiating and integrating sine x and cosh x. So here, if we wanted to differentiate this function, e to the 2x cosh x, there is a method which I'll show you a little bit later, where we could replace cosh x with e to the x plus e to the minus x over 2 and use the exponential function, but I'm going to show you the method to differentiate this using a product rule. So we've got u and v, and I'm going to do f dashed x using a product rule. So we've got differentiate u using the chain rule, leave v plus leave u, differentiate v, and if you differentiate cosh, we now know that we get sine x. Now if I go to the definition of cosh x and the definition of sine x, we can start to simplify this. So I'm going to pull out a common factor of a half e to the 2x, and we should have then 2e to the x plus 2e to the minus x plus e to the x minus e to the minus x. So now collecting like terms gives us a half e to the 2x, 3e to the x plus e to the minus x, and that can be written in a slightly neater form of e to the x. If I take one of the exponentials inside this bracket, I get 3e to the 2x plus 1. So here we solve careful use of the product rule in order to differentiate e to the 2x times cosh x and to get to this version of the answer. Here we can see an alternative approach where I've replaced cosh x with e to the x plus e to the minus x over 2. The advantage of this method, once you've expanded the brackets, is I don't need to worry about product rules anymore. I just need to watch out for that chain rule there. The form in which you are required to give the final answer kind of depends on the nature of the question and the requirements of the problem. So now we're going to find the exact area under this curve from x equals 0 to x equals ln 2, and the curve is sine 2x. So the area we're looking for is there. So to find this area, I need to integrate sine 2x with respect to x from 0 to ln 2, which equals integrate sine 2x is cosh 2x, but in order to balance it up we need a half there, so it's a half cosh 2x from 0 to ln 2. And there's a couple of ways of approaching this. One approach is to use your hyperbolic definition of cosh 2x, so this would become e to the 2x plus e to the minus 2x over, and there's a half already, so it would become a quarter from 0 to ln 2. Or the other approach is simply to put the limits in as they are now and get a half cosh of twice ln 2 minus a half cosh twice nothing. So this approach on the right is basically using your hyperbolic definitions on a calculator, for example, and the approach on the left is to use your fundamental definition of cosh. So I'm going to carry on with the approach on the left to show you how it would work if we were using this approach. So subbing in the top and the bottom limits now. So we're going to have a quarter of the top limit going in is e to the twice ln 2 plus e to the minus 2 ln 2. Take away a quarter, bottom limit going in, e to the nothing is 1 plus e to the nothing is 1 again. E to the 2 ln 2 is e to the ln 4, so there's a power law, and we're going to do a similar thing here. E to the minus 2 ln 2 is e to the ln a quarter minus 2 quarters. So we have a quarter of e to the ln 4 is 4. Remember, e and ln are inverse functions of each other, and e to the ln a quarter is a quarter. Take away a half, gives us the answer 9/16 is the exact area bounded by the curve sine 2x from 0 to ln 2. And if you'd done it on a calculator, you would have got exactly the same answer of 9/16. So the one approach I use, so I integrated sine 2x carefully using cosh 2x over 2, make sure you balance it up. And the approach I used was to write cosh 2x in terms of its exponential definition, but we could have done it by subbing the limit straight in and using a calculator. And that found the shaded area. So that brings us to the end of Hyperbolic Functions 1, an introduction.